Hello, dear students. Welcome to the playlist and welcome to the channel. So, in this new playlist, we have started discussing about the protection against the over voltages. We have discussed about the voltage surge in detail in the previous class. We have discussed what is a voltage surge, how the voltage surge or transient voltage gets produced, and we have seen what happens when such voltage surge is takes place in my power system. We have seen different type of causes, what are the components or what are the different things which causes this over voltages. So we have studied them in detail as well. Basically there are two type of causes. First one is called internal causes and second one is called external causes. We have seen both of them in detail, and after that we have discussed a little bit about lightning. We have discussed what is a lightning and how does it gets produced. We have discussed the mechanism of lightning discharge in detail. We have seen various ways that lightning can produce and how does it affects the power system, that we are going to see next. Typically we are going to see today the most popular topic of um, power system. If we are into natural phenomena, different type of lightning strokes. So few of you might not have imagined that there can be different type of lightning stroke, but there are different type of lightning strokes, basically called direct stroke and indirect stroke. So we are going to discuss that in detail today. But before I start, I must give you advice that in order to understand this lecture, you must it would be better if you are familiar with what is a lightning and how does the lightning gets produced. So it will be better for your understanding. You will be able to grasp the concept much quickly if you are aware of that. And no need to worry, you don't have to go anywhere else to understand that. We have covered it in the previous video. So if you have not checked the previous video, the link will be flashing on the top right hand side corner of the screen in the I button, so you can just click on it and see the video and then continue from here. But in case you have seen it already, let's move forward and let's discuss how the lightning strokes gets produced and what are the different type of lightning strokes. So I've already disclosed that there are basically two type of lightning strokes. First one is called direct stroke and second one is called indirect stroke. And based on their name you can guess that what are this is not very difficult to guess that what is a direct and what is indirect stroke. But how do they get produced and which one of them is more dangerous, and how do we protect our system from this type of strokes is more important. So we are going to discuss that, and that holds the more importance as well, right? So first one, let's start with the direct stroke. The direct stroke, um, what happens in that, the lightning discharge, like whatever the path of the current will be follows. If you remember the previous class, the lightning discharge is directly from the cloud to the subject equipment. Okay, equipment, by the word subject equipment I mean it will fall on either of your equipment of your power system. Okay, like it can be an overhead line. Let's assume it is an overhead line, right? So if it falls on an overhead line, so from the line, current path may be the maybe over the insulators down to the pole to the ground. Okay, so all right, apologies for the disturbance. So we were talking about the direct stroke. How does the direct stroke gets into the action, right? So when it strikes the overhead line, the path which will be followed will be from the line. The current path will be go to the insulator and down to the pole to the ground. So the over voltages set up due to the stroke can be very large to flash over the path directly to the ground itself. And based on that, not based on that exactly, but direct stroke can also be diverted or classified in two different type of strokes named type A direct stroke and type B direct stroke. Okay, so among them, let's first discuss what are the type A direct strokes. So here on the image which is given on the left hand side is showing you the type A direct stroke or stroke A, let's call it stroke A. So what happens in stroke A, the lightning discharge which is coming from the cloud to the subjective equipment or my transmission line or overhead line will, the lightning discharge will fall on the overhead line itself directly. How? So the cloud will induce the charge of opposite sign on the tall object, in this case the overhead line, which is a tall object indeed. So when it will induce the charge, when the potential between the cloud and the line exceeds the breakdown value of the air, the lightning discharge will occur between my cloud and my overhead line. Pretty much simple, right? There is nothing new in this. It is very simple. Now, stroke B is little complicated than stroke A, but not too complicated. It is still easy to understand. Let's see what is stroke B. So, in stroke B, the lightning discharge occurs on the overhead line as a result of stroke A between the clouds. Okay, so let me repeat it one more time. Lightning discharge occurs on the overhead line as a result of a stroke A between the clouds. As you can see here, we are having three clouds: cloud P, cloud Q, and cloud R. So cloud P is positively charged, Q is negatively charged, and R is positively charged again. Okay. Now what will happen? The charge on the cloud Q is bound by cloud R. Okay, so cloud Q, charge of the cloud Q is bound by cloud R, and if the cloud P shifts too close to the cloud Q, then the lightning discharge will occur between cloud P and cloud Q, between the clouds which are moving closer to each other. And then the lightning discharge will occur, and then the charges of both of these clouds will disappear quickly. And because of this disappearance of these charges, the result is that the charge on the cloud R will suddenly become free, because the cloud because R and Q are linked, right? So because Q's charge has been dissipated, so the charge on the R is free suddenly. All of a sudden, it is free, and because as it is free, the result is that the charge on the cloud R will suddenly become free, and it discharges rapidly to the earth. So in such case, it will completely ignore the tall object. It can fall anywhere. Okay, it can fall anywhere. Like the direct strokes on the power system are very rare, but uh, stroke A can fall on tall objects. So most of the times, if stroke A is happening, then it will fall on the tall objects, and we can protect the tall objects from such kind of strokes, like strokes like stroke A. But if stroke B is taking place, then there is no way that you can protect your power system, because stroke B will not fall on the tall object. It will fall anywhere. It can fall on the ground itself as well, right? So it stroke B completely ignores the height of the object, and it can strike on the ground or anywhere else. And because of that, it is quite impossible to provide protection against the stroke B. Then there is another type of stroke. This was the direct stroke. Now let's discuss about the indirect stroke. So indirect stroke results from the electrostatically induced charges on the conductors due to the presence of charged clouds. See this image. You can see a positively charged cloud above my overhead line, right? And because of this positively charged cloud, there is a negative charge getting induced only below where the cloud is on my overhead line, right? This is happening because of electrostatic induction. The negative charge, however, will be only on the portion of the line right under the cloud, and on the other places there is nothing, you can see. But again, see on the corners, right? We are seeing the positive charges. So the positive charges leak slowly to the earth via the insulators. So when the cloud discharges to the earth, to another cloud, the negative charge in the wire is isolated. You can see, because we are having positive charges over here, so negative charge is isolated, and we are having positive here, so what will happen? The positive will attract the negative, right? So so the cloud has been discharged to the earth, right? Which means the induced positive charges which were leaking now are attracting the negative charges. So when the cloud discharges to the earth or to another cloud, whenever it wants to go, the negative charge on the wire is isolated, as it cannot flow quickly to the earth over the insulators. And because of that, the result is that the negatively charged negative charge rushes along the line in both the directions, because it is getting attracted by the positive charges. So it quickly will rush along the line in both directions in the form of traveling waves. And because it is moving as a traveling waves, majority of the surges in the transmission lines are caused by such type of strokes, indirect lightning strokes. Okay, because we have already discussed that direct lightning strokes are very rare. So most of the lightning strokes which occur in the power system are these type of strokes, indirect strokes, in which actual lightning is not falling on my object, but this negative charge which is gathered on the overhead transmission line or distribution line is leaking the negative charge quickly, very quickly, right? So we can protect our power system from this lightning strokes. But before we discuss that, let's discuss how much harmful this lightning can be, right? Either be it direct or indirect, lightning stroke on the transmission line will produce a steep fronted voltage waves on my transmission line, and the voltage of this wave can rise from 0 to its peak value. Peak value can go around towards 2000 kilovolt as well, right? You understand how dangerous it can be, and that too in only 1 microsecond, and decay to the half peak value in about 5 microseconds. So it is very transient process, it happens very quickly, but too much voltage and it will destroy your system. So such steep fronted voltage wave will initially travel through the line waves along the line in both directions, with the velocity depending upon the value of your capacitor and inductors, the value of capacitor and inductors of your transmission line or distribution line, subjective line, in short. So the traveling waves which are produced due to the lightning surge will shatter the insulator and may even wreck your poles. So it is completely, like, it will completely destroy your insulators. And if the traveling waves are produced due to the lightning hit the winding of the transformer or your generator, it may cause considerable damage. How? Let's see. Let's say we have a transformer, and the induce of the winding opposes any sudden passage of electrical charge through it, and therefore the electrical charge piles up against the transformer, right? Because the inductance was opposing the sudden passage of electric charge through it, and because of that, in my transformer the electric charge is piling up against the transformer. So this induces such an expensive pressure between the windings that the insulator may break down, and resulting that, what we have, we get production of an arc, and it is more destructive. How? So while the normal voltage between the turns is never enough to extinguish an arc, But once the insulation has broken down and an arc has been generated by any momentary over voltages, then whatever the line voltages are, the line voltages is usually sufficient enough to maintain that arc long enough to severely damage your transformer. Same thing can happen in generator or any other machines as well, right? So it is very dangerous for your transformer, generator, or any other machines. In the arc, if my arc is initiated in any part of the power system by any kind any type of lightning stroke, this arc will set up very disturbing oscillations in my line. And because of that, if we don't um, control it control it quick enough, then this may damage the equipment connected to the line itself as well. So it will give us a lot of physical harm to my power system, not only overhead line but other equipments or other apertures connected to it as well. And because of that, it is very important to provide the protection against the lightning to my apertures, to my equipments. So how do we do that? Let's see. We are going to see that now, how the protection against the lightning can be provided. So the transient or surges on the power system may originate from switching and from other causes, but the most important and dangerous surges are those which are caused by lightning. We just saw that a minute ago. The lightning surges may cause the serious damage to expensive equipment in the power system. It can be anything. It can be generator, it can be transformer, it can be potential transformer, it can be current transformer, it can be anything. So either by direct stroke on the equipment, or the stroke on the transmission line, or stroke on the transformer, anything that can equipment stroke on the any kind of equipment that reaches the equipment as a traveling wave. So it is important to provide protection against both kind of surges, direct and indirect. And for that purpose, we use three type of protection devices. First one is called earthing screen, second one is called overhead ground wires, third one is the lightning arrestor or surge diverter. If you are not familiar with it, let me give you a small glimpse, and then we will be discussing about each of them in detail today. So first one is the earthing screen. Earthing screen provides a protection to power station and substations against the direct stroke, whereas the second one, the overhead ground wires, protects the transmission lines against the direct stroke. Then we have the lightning arrestor or surge diverter, which protects the station apertures against both direct and indirect strokes that come into the apertures as a traveling waves. So let's discuss each of them in detail. The first one is the earthing screen. So the power station or substations generally house expensive equipments, right? There is this is not a new news or big news to us. We all know that how costly it is to erect a whole substation or whole power station. It is very costly, very expensive. So these stations can be protected against the direct lightning strokes by providing earthing screen. Again, I'm talking about the direct strokes only. I'm not talking about the indirect strokes here. And how can we do that? So what that lies in the construction of the earthing screen. The earthing screen consists of a network of copper conductors, and these network of copper conductors is normally known as copper shield or copper screen, which is mounted all over the electrical equipments in my substation or my power station. This shield is properly connected to the earth on at least 2 points through the low impedance. So what happens is, whenever the lightning stroke charges on your equipment, charges on your power station or substation, this earthing screen provides the low resistance path to the lightning stroke, by which the lightning surge are conducted to the ground. And in this way, the station equipment can be protected against any kind of damages, right? But there is a limitation. As I've said, it can only give you protection against the direct lightning strokes. There is no way that this screen can give you the protection against the indirect strokes. And one more thing, that it cannot give you protection against type B type of direct lightning strokes. But there is no way that you can provide protection against type B type of lightning strokes using any kind of equipment. So uh, we will not consider it as its limitation. uh, and as it is not providing the protection against the indirect lightning strokes, we can also say that it cannot provide the protection against traveling waves, which may reach the equipment in the station. Now let's see the second, the overhead ground wires. It is very easy and very simple to understand with the help of a picture. And it also happens to be the most effective method of providing protection to my transmission line against direct lightning strokes. So as you can see in the picture, for simplicity, one ground wire and one line conductor are connected with my transmission line. The ground wire, as you can see, is placed above the line conductor at such position that the practically all lightning strokes are intercepted by them only, right? By whom? By ground wires. So the so the ground wires are grounded at each tower or pole through as low resistance as possible. So due to their proper locationing, the ground wires will take up all the lightning stroke instead of allowing them to uh, go through them and strike the line conductors. So what ground wires are doing, the ground wires are just like our parents. Just the way our parents, in whenever you were when you were little, when you were a kid, your parents used to take all the blame on themselves, right? They used to do all the work. Just like that, ground wires protects the line conductors. Or you can consider it like the military, who are there on the border and protects us, the people who are living inside of the country, right? So ground wire does that job. And by doing that, it protects the line conductor. So when the direct lightning stroke occurs on the transmission line, it will be taken up by the ground wires. So the heavy lightning current, like 10 ampere, 10 kiloampere to 50 kiloampere from the ground wires, uh, that will flow from the ground wire, right? It will flow from ground wire to the ground, and by doing that, you are protecting the line from harmful effects of lightning. And again, the degree of protection. So sincere apologies for the disturbance again. Now we were discussing that the degree of the protection which is provided by the ground wire depends upon the footing resistance of the tower as well. How much value does it hold, right? What How much value of footing resistance of the tower is. Let's say, for example, the tower footing resistance is R1 ohms, and the lightning current from the tower to the ground is I1 amperes. Then the tower rises to the potential of V1, and this V1 will be equal to I1 into R1. And now, since the V1 is the approximate voltage between the tower and the line conductor, this is also the voltage that will appear across this striking the it will appear across the insulators. And if the value of V1 is less than the required to cause insulation flashover, then there is no trouble at all. But if it exceeds the of um, value which required to cause the insulation flashover, then the insulator flashover may occur. and because of V1 is dependent on the tower footing resistance R1, the value of the resistance must be kept as low as possible to avoid the insulator flashover. So by keeping that value very low, we can avoid the insulation flashover. Now, what are the advantages of overhead ground wires? So first one is that it provides the considerable protection against direct lightning strokes on transmission lines. Second one, the grounding wire which is providing us damping effect on any disturbance traveling along the line, as it acts as a short circuit secondary. And also it provides a certain amount of electrostatic shielding against the external fields as well. So it reduces the voltage induced in the line conductors due to the discharge of the neighboring clouds as well. Now, what are the disadvantages? So first one is the cost, because you need the whole ground wire, you need to ground it through the poles, so its cost is very high. Second one, there is a possibility of its breaking and falling across the line conductor, so thereby causing a short circuit of faults. And this objection has been greatly eliminated by the galvanized stranded steel conductors as a ground wires. This provides sufficient strength to the ground wire as well because of this galvanized stranded steel conductors, right? Now the third point, or the third type of protection which we provide against the lightning, is lightning arrestor. So the earthing screen and ground wires can well protect the electrical system against the direct lightning, but they fail to provide the protection against the traveling waves which may reach the terminal apertures. The lightning arrestor or surge diverter provides a protection against such surges. So a lightning arrestor or a surge diverter is a protection device which conducts the high voltage surges on the power system to the ground. So first let's see the construction of a lightning arrestor. So as you can see in this figure, the basic form of surge diverter is shown in this figure, the first figure on the left hand side I'm talking about. It consists of a spark gap in series with the non-linear resistor. As you can see, we are having a spark gap here and we are having a non-linear resistor over here. One end of the diverter is connected to the terminal of the equipment to the protected equipment to be protected, as you can see here, and the other end is effectively grounded, which is pretty much visible over here. The length of the gap is so that the normal line voltage is not enough to cause an arc across the gap, but dangerously high voltage will break down the air insulator and will form an arc. And the property of this non-linear resistance, due to the non-linear resistance, is that the resistance decreases as the voltage increases and or the current increases, and vice versa, right? If the voltage and current are increasing, the resistance will also increase. The voltage and current are decreasing, the resistance will also decrease. So now let's see how does it work. So first let's talk about the normal conditions. Normal operation, the lightning arrestor is off, which means it doesn't conducts any current to the earth because the gap is non-conducting. But when overvoltage occurs, the air insulation across the gap breaks down and the arc will be formed. Now this arc will provide now the low resistance path will be provided for surge to ground, and in this way the excess charge on the line due to the surge is harmlessly conducted through an arrestor to the ground instead of being sent back over the line. So it will let the current through. Then the function of the non-linear resistor in the operation of the arrestor is very important, as the gap sparks over due to the over voltages. The arc would be short circuited on the power system and may cause power follow current in the arrestor. And since the characteristics of this resistor is to offer high resistance to the high voltages, it prevents the effect of a short circuit. Once the surge is over, then the resistor offers the high resistance to make the gap non-conducting. So it is pretty much straightforward. Now, two things must be taken care of in the designing of lightning arrestor. First thing, when the surge is over, the arc in the gap should cease. If it fails to cease, then the current will continue to flow through the resistor, and both resistor and the gap, spark gap, will be destroyed, which means your lightning arrestor will be destroyed. Secondly, the IR drop, where uh, where we are considering the surge current as I. So this IR drop across the arrestor when carrying surge current should not exceed the breakdown strength of the insulator of the equipment to be protected. Right? If it exceeds that breakdown strength, then there is no point. Right? It's pretty much self-explanatory. Now we are due to discuss about the type of lightning arrestors, but we are running out of time here, so we will stop today's class here. In the next class, we are going to discuss about the types of lightning arrestor, and we are going to discuss in detail about different type of surge arrestors as well, or not surge arrestors, surge absorbers as well. And that hopefully will be the last class of this chapter or this playlist. So I will be seeing you in the next class. Thank you very much for listening and take care of yourselves. Goodbye for now.